Imagine being able to leave Earth and rise. Rise until the ground disappears, until the clouds look small like tufts of cotton. The blue atmosphere dissolves, and before you appears space, silent, vast, speckled with stars. Earth is now just a blue sphere floating in the darkness, circling a medium-sized star we call the Sun. But what if we kept rising? What lies above and below the solar system? Where does our cosmic neighborhood end? This simple question invites us to pass through every layer of the cosmos, as if we were a camera pulling back in an endless zoom-out. And that's exactly the journey we'll take now, from Earth's surface to the edge of the observable universe. Our starting point is the Sun, the heart of the solar system, a star 1.4 million kilometers across, made mostly of hydrogen and helium, where nuclear fusion turns matter into light and heat. Every second, the Sun releases more energy than all of humanity would consume in a million years. It accounts for 99.8% of the solar system's mass, and its gravity keeps everything, planets, moons, asteroids, dust, and comets, in a delicate balance. If we observe the solar system from far away, we'd see a flattened disk, like a vinyl record floating in space. This disk is called the ecliptic plane, and it's where almost all the planets orbit. The reason is simple. The solar system was born from a rotating cloud of gas and dust around a dense center. Over time, the rotation flattened that cloud into a disk, and from that material, the Sun and the planets formed. Within this disk, we find the rocky planets: Mercury, Venus, Earth, and Mars. They're small, solid, and relatively close to the Sun. Mercury is a world of extremes. On one side, temperatures reach 430 degrees Celsius. On the other, minus 180 degrees Celsius. Venus is shrouded in an atmosphere so dense that surface pressure is 90 times that of Earth, like being a kilometer under the sea. Mars, in turn, is cold, reddish, and silent, but with clues that it once had rivers and perhaps entire lakes. Between Mars and Jupiter lies the asteroid belt, a region filled with rocks and debris left over from planetary formation. Many imagine a chaotic field of boulders, but in reality, space is vast. Asteroids are separated by millions of kilometers. Ceres, the largest of them, is a dwarf planet about 940 kilometers in diameter, a mix of ice and rock, possibly containing a subsurface ocean. Continuing outward, we cross into the realm of the giant planets. Jupiter, the colossus of the solar system, is 1,300 times larger than Earth. Its atmosphere swirls with eternal storms, and the Great Red Spot, one of them, is so large that 3 Earths could fit inside. Next comes Saturn, with its magnificent rings made of ice and dust. Uranus and Neptune round out the group, cold, distant worlds swept by winds up to 2,000 kilometers per hour. Neptune, the outermost planet, orbits the Sun at a distance of 4.5 billion kilometers. But the solar system doesn't end there. Beyond Neptune, we find a fascinating region called the Kuiper Belt, an annulus of ancient icy bodies left over from the solar system's origin. Among them is Pluto, which stopped being classified as a planet in 2006 but remains one of the most intriguing worlds ever discovered. Its valleys of frozen nitrogen and ice-capped mountains reflect a bluish light, like a distant mirror. Other residents of this belt include Haumea, with its elongated shape and rapid rotation, Makemake, coated in frozen methane, and Eris, almost the size of Pluto. Leaving the Kuiper Belt, we enter the scattered disk, where objects follow much more elongated orbits. That's where Sedna lives, a dwarf planet with such an eccentric path that it takes more than 11,000 years to complete one trip around the Sun. At this point, the Sun is just an ordinary star in the sky, a bright point like the others, indistinguishable unless we know where to look. Continuing our ascent above the ecliptic plane, we reach the boundary where the Sun's influence begins to wane. Here, space is dominated by subatomic particles traveling at extremely high speeds, the solar wind. It blows constantly outward from the Sun, forming a gigantic bubble that envelops the entire solar system, the heliosphere. It's as if the Sun lived inside an invisible bubble made of its own breath. This bubble extends to about 18 billion kilometers from the Sun. There, the solar wind loses strength and collides with the interstellar medium, the gas and dust that fill the space between stars. This boundary is called the heliopause, and it marks the true limit of the Sun's domain. It was exactly this limit that the Voyager 1 and 2 probes crossed. Launched in the 1970s, they visited the giant planets and then headed into the unknown. Today, they continue sending faint signals, traveling through regions no human has ever seen. Voyager 1, for example, has already gone beyond 24 billion kilometers from Earth, and every second it grows more distant. Its instruments detected the moment when the solar wind ceased and space became different, colder, denser interstellar space. It was the first time we touched the outside of the solar system. But there is something even more distant, something that surrounds everything we've mentioned so far: the Oort Cloud. It's an immense sphere of comets and frozen fragments that encases the solar system in all directions, like a cocoon. It's estimated to extend to 100,000 astronomical units, or about 1.5 light-years. It's such a remote region that a comet coming from there can take millions of years to return. This cloud is both the graveyard and the cradle of comets. Some are expelled by the gravitational tides of neighboring stars. Others fall toward the sun, lighting Earth's sky with long tails of ice and dust. And so, when you finally leave the Oort Cloud, you are officially outside the solar system. The sun, from so far away, is nothing more than a bright star among billions. Earth, invisible. Jupiter, Saturn, Pluto, all gone. What lies above and below now is interstellar space, the void between the stars. Now that we've left the solar system behind, we are immersed in the interstellar medium, an almost empty ocean, yet not entirely devoid of matter. Here there are dispersed hydrogen atoms, thin clouds of gas and dust, and even subtle magnetic fields stretching across light years. If we could see the interstellar medium in infrared, it would look like a luminous mist, crisscrossed by denser regions called molecular nebulae, the birthplaces of stars. The Sun, along with dozens of nearby stars, moves within one of these structures, the so-called local bubble. Imagine a vast cavity in the middle of the galaxy, about 300 light-years across, sculpted by ancient supernova explosions. Those supernovae swept away gas and dust, creating a rarefied region where space is cleaner. It's inside this bubble that the solar system travels, at about 220 kilometers per second, slowly orbiting the center of the Milky Way. And even this bubble isn't isolated. It connects to others, forming tunnels and cavities, as if the galactic disk were a cosmic sponge full of bubbles of heated gas. Above and below this region, other stars begin to appear. Alpha Centauri, our nearest stellar system, is 4.3 light-years away, and is in fact a trio of stars: Alpha Centauri, A, B, and Proxima Centauri, a small red dwarf that hosts a potentially habitable exoplanet, Proxima b. And if we zoom out further, we begin to see the structure they belong to: the Orion Arm, one of the many spiral arms of our galaxy, the Milky Way. The Orion Arm is a swath of stars and nebulae stretching about 10,000 light-years. This is where the Sun and its neighbors reside, a privileged location, neither too close nor too far from the galactic center. In a sense, this position is ideal, far enough to avoid dangerous regions of intense radiation and stellar crowding, yet close enough to host heavy elements forged by previous generations of stars. As we rise above this spiral arm, the galaxy's shape begins to reveal itself. The Milky Way is a colossal disk about 100,000 light-years in diameter and only about 1,000 light-years thick, astonishingly thin compared to its width. If the universe were scaled so that the galaxy were the size of a dinner plate, the solar system would be smaller than a speck of dust. Seen from above, the Milky Way is a spiral with 4 main arms, slowly rotating around a bright core. That core, known as the galactic bulge, contains billions of aging stars and a supermassive black hole called Sagittarius A*, with more than 4 million times the mass of the Sun. This black hole is the galaxy's gravitational heart. Everything orbits it, including the Sun, which completes one lap every 230 million years. Around the galactic disk lies a tenuous region called the galactic halo. The halo contains ancient stars, globular clusters, and a vast amount of invisible matter, dark matter. This matter doesn't interact with light, but its presence is detected through gravity. It's what keeps stars in their proper orbits, preventing the Milky Way from flying apart. Without dark matter, the galaxy would simply disintegrate. As we continue to rise, the galactic disk turns into a thin line of light. The glow of its stars blends into a faint whitish band. This is what we see in the night sky as the Milky Way, the luminous trail that cuts across the firmament. But from the outside, the view is indescribable. Billions of stars, interstellar dust, nebulae, clusters, planets, and black holes, all turning in a silent, eternal cosmic choreography. But hold on, we're not done yet. Beyond the galaxy, we find even larger structures. The Milky Way isn't alone. It belongs to a group of neighboring galaxies called the Local Group. This group contains more than 50 galaxies bound by gravity and spans about 10 million light-years. Among them, the largest are Andromeda, M31, and Triangulum, M33. The Milky Way and Andromeda are the giants of this group, and they're on a collision course, a gravitational dance that will, about 4 billion years from now, end in a colossal merger forming a new elliptical galaxy astronomers already call Milky Way. Within the Local Group, there are also dozens of dwarf galaxies, small collections of stars like the Magellanic Clouds, visible to the naked eye from the southern hemisphere. These galaxies orbit the Milky Way like cosmic moons, slowly being distorted by its gravity. In fact, there are already streams of stars, called tidal streams, formed from the remnants of these smaller galaxies being absorbed. But the Local Group, large as it seems, is just a drop in an even vaster ocean. It's part of the Virgo supercluster, an immense collection of thousands of galaxies distributed across dozens of clusters. At the center of this supercluster lies the Virgo cluster, with about 2,000 galaxies, including giants like M87, which hosts a black hole of 6.5 billion solar masses, the very one photographed for the first time in 2019. The galaxies in this cluster are so distant that their light takes 60 million years to reach us. In other words, when we observe them, we see them as they were when dinosaurs still walked the Earth. And this Virgo supercluster, in turn, is only part of something even larger, the Laniakea supercluster, a Hawaiian word meaning immense sky. It's one of the largest structures known in the universe, encompassing more than 100,000 galaxies and stretching some 500 million light-years. The Milky Way is just one of many that slowly flow within this gigantic gravitational network. Astronomers have discovered that galaxies inside Laniakea aren't stationary. They move along paths that converge on a dense region called the Great Attractor, a mysterious concentration of mass that pulls everything around it. At this point, the scale becomes almost impossible to imagine. Above and below, in every direction, there are billions of galaxies. The Milky Way, which once seemed infinite, is now just a particle within a colossal web. And, most surprising of all, this web isn't uniform. On large scales, the universe is made of filaments, threads of galaxies connected by gravitational bridges, and voids, almost empty regions hundreds of millions of light-years across. These structures form what cosmologists call the cosmic web, the three-dimensional architecture of the universe. Imagine an even greater zoom out. You'd see something like a giant sponge made of light. The filaments are the sponge's edges, and the voids are its hollow spaces. Every bright point in this structure is a cluster of galaxies. Each galaxy contains hundreds of billions of stars, and practically all those stars have planets. Each point then represents an ocean of worlds. At this scale, it becomes nearly impossible to think in terms of above or below. Space loses direction. There's only depth, immensity, and time. We're now so far away that it's impossible to recognize any point of origin. The Sun, Earth, the Milky Way itself, everything has vanished, diluted among billions of galaxies. Before us, the universe reveals itself as a vast network of light and shadow, a cosmic web where each filament is a stream of galaxies and each node is a colossal cluster. This structure spans billions of light-years and represents the grandest pattern of cosmic order, the skeleton of the universe. Astronomers call these immense formations filaments. Between them lie cosmic voids, regions of near-zero density where there are so few galaxies that space looks completely bare. One such void, the Buddha's void, is about 330 million light-years in diameter, and within it there are only a few dozen isolated galaxies, lost in an abyssal nothingness. It's hard to even imagine the silence of such a place. If a civilization lived there, it would see very few stars in the sky. Perhaps it would believe it was alone in the universe. Filaments, on the other hand, are the highways of matter. They're made of galaxies, gas, and dark matter bound together by gravity, and collectively they form a structure reminiscent of an ant colony, with trails that intersect at luminous hubs. One of the largest filaments ever detected is the Sloan Great Wall, a cosmic wall more than 1.3 billion light-years long. Even larger is the Hercules Corona Borealis Great Wall, a structure that stretches roughly 10 billion light-years, considered the largest ever observed. These dimensions even challenge cosmological models, because on such gigantic scales, the universe should look homogeneous. Yet, these walls show it still harbors unexpected complexities. Above and below these filaments, there is no sky or ground. The universe is three-dimensional and centerless. There's no reference point, no north, no cosmic south. The expansion of the universe happens equally in all directions. We're not in a special place, but at just one location within an immensity that extends without apparent boundaries. By now, our zoom out reaches the full scale of the observable universe. Everything humanity has seen and measured is contained in an imaginary sphere about 93 billion light-years in diameter. This limit isn't physical, it's temporal. It represents the maximum distance light has had time to travel since the cosmos was born, 13.8 billion years ago. So when we look to the universe's farthest reaches, we're looking into the deepest past possible. Each distant point is a time machine, showing how the cosmos looked at different moments in its own history. Within this sphere are around 2 trillion galaxies, each with hundreds of billions of stars. And around those stars, trillions of worlds orbit, some rocky, others gaseous, some perhaps covered in oceans, and others frozen forever. It's almost inevitable to imagine that, somewhere, there is life looking back, trying to understand the same mystery. But what lies beyond this limit? This is one of the most fascinating and challenging questions in modern cosmology. The observable universe is just a part, perhaps a tiny one, of something much larger. According to the inflationary universe model, space not only expanded after the Big Bang, but continues to expand today, accelerated by what we call dark energy. This expansion means there are regions so distant that their light will never reach us, no matter how long we wait. They're beyond our cosmic horizon, invisible and unreachable. There may be other galaxies, other cosmic webs, perhaps even other entire universes beyond that boundary. Some physicists entertain the idea of the multiverse. According to this hypothesis, our universe would be just one bubble among countless others, each with its own physical laws. Some might have more spatial dimensions, others, different fundamental constants. Perhaps some collapsed quickly, and others expand forever. And it may be that we can never cross the boundary between them, just as a fish inside an aquarium can't see the other aquariums around it. But let's return to what we can observe. At the most distant edge of the visible universe, there's a faint, uniform glow coming from all directions. It's the cosmic microwave background radiation, the echo of the Big Bang. This radiation is like a photograph of the universe when it was only 380,000 years old, a cosmic baby wrapped in a haze of hot particles. When that haze cleared, light could finally travel freely. And it's that light we still see today, stretched by the expansion of space into the microwave range. Each bright spot on this map represents small temperature variations, the seeds that, over time, gave rise to galaxies, stars, and planets. This is the final frontier of human observation. It's the most distant moment in time and space we can reach. Beyond it, there are only hypotheses, equations, and imagination. Now, if we reverse our gaze and start to come back, we'll see the universe contract before us. Walls of galaxies become filaments. Filaments become clusters. Clusters condense into superclusters. And soon the Milky Way shines again, like a luminous island in the dark. Drawing closer still, the sun reappears, a small point among billions. The planets return: Neptune, Saturn, Jupiter, and finally Earth, this small blue world suspended in the void. Here, we end our journey. From the sun's warmth to the absolute cold of intergalactic space. From the cradle of a planetary system to the edge of the observable universe. And in the end, we realize that the question, what lies above and below the solar system, takes on a new meaning. Above and below are just directions within an infinite geometry. What truly exists is scale, ever larger and more complex levels of reality, all interconnected by gravity and time. What lies above the solar system is the galaxy that shelters us. Above that, the supercluster that contains it. And beyond, the cosmic web, the primordial radiation, the very fabric of space-time. Below the solar system, on the other hand, are the particles that make up everything: atoms, protons, quarks, the fundamental bricks of matter. The universe is a mirror of scales, and in both directions, infinity seems to repeat itself. And the most astonishing part is realizing that, within this vast system, humans are one of the few known forms of consciousness capable of understanding it all. We are made of the same atoms that shine in the stars, and it's precisely this connection that allows us to grasp the cosmos. When we look at the sky, it is the universe observing itself, trying to understand where it came from and where it's going. Perhaps the true above is the unknown, what we have yet to discover, and the true below is what we've already come to understand. The search for answers is what keeps us moving, what keeps the flame of curiosity burning that brought us this far. Because deep down, the story of the universe and the story of humanity are the same story, the story of a cosmos learning to know itself. While the Voyager probes continue their path toward the stars, the sun carries on its quiet journey around the galaxy. And we, temporary inhabitants of this small blue dot, keep looking up, not just in search of answers, but in search of ourselves. What lies above and below the solar system, the entire universe, and within it, our desire to understand it. If this video made you feel small before the immensity, yet part of it at the same time, then leave a like, subscribe to the channel, and share. Because here, with every new journey, we keep exploring the infinite, together. And as long as curiosity exists, the universe will never stop speaking to us. Thank you for watching, and see you in the next video.